Hello everyone, my name is Murmay Behere and I am from team 18031 Hawktoxes. Today, I'm going to talk about the PID control system and its algorithm. A control system is a mechanism through which a system's state can be controlled. Its components include a sensor, a controller, and a given system. The sensor measures a value from the system, say the temperature of a room or the encoder position of a motor. And using the set point, which is the desired value, it calculates an error, which is passed on to the controller. The controller processes this error and gives a control output, which is what is used by the system to change its state. This is a continuous feedback loop, meaning any change that is seen within the system is acted immediately upon by the controller. Of course, the controller also handles any external disturbances that might be introduced into the system. PID is a control system. It is used heavily in robotics as well as in other fields. Its main pro is that it can be used when the target is changing. It is also a very good system for stable operations. It is made up of three parts: a proportional component, an integral component, and a derivative component. I'll talk about these shortly. The PID system needs to be tuning, which is the gains of these three components need to be tuned to an optimum value for the system. So the proportional component is the component that is the main driving force behind the motion. It produces an output that is proportional to the error in your system. So if your motor has a lot of encoder text to cover, the proportional output will be high. Correspondingly, if your error is very small, which means you're very close to your target position, then your proportional output will be very low. The problem with an only proportional system is that if your KP is too high, then it can lead to overshooting the target. And if your KP is too low, it will take too long to get to the target. And it will cause steady state errors, which is there's a very small amount of error left, which the proportional output is too small to correct. This is where the integral comes in. The integral adds up the continuous errors that is being calculated at each time step, and by multiplying with the Ki, produces the integral component. This means that if you have a continuous steady state error, the integral component will continue ramping up the power until that error is gone. The integral, however, can lead to oscillations, to periodic oscillations. Therefore, you need to remember to reset the integral sum when you reach the set point. The derivative component acts to counteract oscillations and overshoot. What it does is it looks at the rate of change of your state, which means how fast your state is changing, how fast your motor is moving, or how fast your temperature is changing. This derivative acts to counteract this motion. So it slows down the velocity of approach, meaning that you can slow down when you reach the target position. It also helps cancel out disturbances and noise, especially rapid ones. So if there's a jerk to the motor, the derivative can act to cancel it out quickly so that the system isn't affected much. I will now move on to a PID simulator to show how these three values can be tuned. This is a PID simulator. The link for this will be provided below. So as you can see, the blue line is the current set point. This is what the red line needs to reach. Red line is the system. If you can see, I can adjust the set point to a lower value. As you can see, because our Kp, Ki and Kd are all 0, the system doesn't react. Let's give it a small bit of Kp to see what it will do now. As you can see, it started to curve more and more towards the system. But it's taking too long, so let's increase the Kp a bit. If you give it too much for Kp, you can see that it's approaching very fast. But it reaches another steady state error. So let's give it some Ki. If we give it too high of a Ki, the system is going to start oscillating as it will do now. As you can see, it has overshot. The green line, which is the control output, is also oscillating wildly. So, let's reduce the Ki to look at the reaction. With a small enough Ki, this output should stabilize. You can also add a Kd to reduce the speed of approach to the line. After this, let's see how the set point reacts to a change. As you know, first the mean driving force will be the P. As you can see, it overshot quite a lot because your D wasn't enough. So here you would increase your D, Kd. As you can see, now the values are going closer and closer. If you increase your D too much, Kd too much, however, the system will take very long to respond. As you can see, if you change the set point, the system and there you go. As you can see, it is causing unstable oscillations if your D was too high. So lower it back to a reasonable amount. And you can see that the values are getting very close to the set point as necessary. Thank you for watching our webinar. Like, share and subscribe to watch more interesting webinars.